SwayamPrabha. Digital India. Educated India.
So, welcome back to another lecture on Introduction to Soft Matter. In the last class, we were looking at these natural timescales, and we had a quick discussion on some of the Indic timescales that had been used, which all came from natural phenomena, right? So, for example, we said that the nimesha is the duration taken for a twinkling, and then you had truti as a time which was taken by a sharp needle in piercing a lotus petal, and there were obviously other time scales like days, lunar months, years. I also gave you the reference from where I got it. This is a text which has been edited by a couple of authors, but it contains essays by many other very prominent writers, so you can take a look at this if you want. We also gave you the relationship between the different time scales. So, obviously, it is not enough to state that these time scales exist, but one has to also give the interrelationship. If there are multiple time scales present, then one has to specify that as well. So, that also was specified. So, why are we discussing this? The reason we are discussing this is because there are many phenomena which do have an intrinsic time scale associated with it. That is one of the take home messages for us, that there is nothing that is instantaneous. Okay? The twinkling of a star is not instantaneous, and neither is the movement of a fluid or movement of a solid. We may idealize it as instantaneous in some cases, but it is truly not. And it is important to understand this idea once we start exploring the idea of viscoelastic materials or soft matter, because we will see that there will be a finite time scale which will be associated with the material's response there. So, this is very good, and I hope you have taken home this simple idea that natural systems have a time scale associated with them. But once again, does it really apply to fluid, to the topic at hand, which is here we are discussing soft matter or viscoelastic materials. So, what I want to do is I would like to show you another manuscript, and this manuscript discusses a very interesting experiment, and it is rather famous, and this is the pitch drop experiment. Okay. And this pitch drop experiment refers to an actual experiment that was carried out and at the Department of Physics at the University of Queensland in Brisbane. And this beautiful experiment here, I just read out the first paragraph perhaps. In the foyer of the Department of Physics at the University of Queensland in Brisbane is an experiment to illustrate, for teaching purposes, the fluidity and very high viscosity of pitch, set up in 1927 by Professor Thomas Parnell, the first professor of physics there. And just to put this in context, this is even prior to the independence of the Indian nation. This experiment is still ongoing, and that is the really interesting thing about it. Now, the reason this experiment is interesting is because it deals with pitch, which in a normal condition, I hope all of you have seen it at some point, being used for road construction, and it is a solid in our normal experience, unless it is melted down, of course. But at normal temperature, it is a solid material. And what they did is they poured this pitch into a glass funnel, and you can see this glass funnel here. This is okay, sorry, that is highlighting the wrong place. I will just go to the arrow. So, this is maybe I will switch to that. So, this is the glass funnel, and pour into it was pitch. This black material is pitch right here. And then somebody cut this stem at some point, and what would you expect? It's a solid material, so you just expect to stay in place, and that's exactly what happens. It stays in place, and maybe you go for lunch, come back, it still stays just like that. But then let's say you are a being who takes a nap of 10 years, and then you come back. You will see that there is a pendant drop that has formed, and that this drop will drop into this beaker below. So somebody started to make a record of when the drops fell. It's a meticulous experiment because you can see the time scales involved. 1930, the first stem was cut. 1938, the first drop fell, and so this is about 8 years here. 1947 is the second drop fell, and so on. It lists all the different times, and this experiment, as I said, it's still in progress, so people are still watching it and making a note of when the drops fall. So now imagine, so this is an extremely long duration for a normal human being, right, 10 years. But imagine you are an alien being for whom the nimesha, or the twinkling or the blinking of an eye is now 10 years instead of the normal human blinking time period. What will you see? You will see that the drops of this pitch, which is a solid object for you, for humans, is falling down almost as if it's liquid. In day-to-day human experience, if you have a leaky faucet, you will have these annoying droplets falling from a tap at a very high frequency, and it will seem to you like that. So it's important to set the context of the observation, and the time scale that is involved in the observation is as important in qualifying a material as the material itself. So this experiment was extremely interesting because you could, in principle, look upon this pitch as just as a fluid with a very high viscosity, and actually they have done that work. So this is a very small paper, by the way, it's just 3 pages. I encourage you to just download this and read it for yourself. But just to highlight the important issue here, they show that the viscosity of pitch can be calculated, and it comes out to be some number which is of the order of 10 to the power 8 pascals second. I hope you remember what the viscosity for water is. Just take a second and try to recollect. You don't have to, because it's written right here. So the viscosity of water at normal temperature and pressure is 10 to the minus 3 pascals second. So I hope this shows you the kind of order of magnitude difference, many orders of magnitude difference that exists between these two type of fluids. So this was an extremely interesting experiment because it showcases the idea that the observer is an important person, and the observer sets the context for deciding whether a material is behaving like a fluid or whether the material is behaving like a solid. Now if I had to quickly just go back and to the slides where we had discussed the topic of soft condensed matter is a convenient term for materials and states of matter that are neither simple liquids nor crystalline solids. So what do we mean by simple liquids or crystalline solids? It does not say much about how this definition comes about, or this statement by itself is not enough to clarify what a simple liquid or a crystalline solid is. But there are multiple perspectives on how you can understand solids and fluids. One is obviously the thermodynamic perspective, where you can look at the molecular scale behavior and try to understand the behavior of material from that perspective. The other perspective is the continuum mechanics perspective, where we deal with the behavior of the material or the response of the material to forces. So we in this particular course, and I have to clarify that soft material courses can take various approaches. In this particular course, we will take the approach of trying to understand soft materials or liquids and solids from the perspective of their response to forces. So, when I apply a certain amount of force, some change must occur, right? And it cannot be just a rigid body motion, because we are talking about things that are not infinitely rigid, so, or point masses. So, we are talking about finite bodies. If we are talking about finite bodies, the finite bodies will have a response to the force. And what is the time scale of or the what is the time scale of response of these becomes important, as well as the time scale of observation also becomes important. Okay. So, this pitch drop experiment, I hope it sets the context for the idea that the observer is an important, there is no person, it is not a human being necessarily that is observing it, but however you are doing it experiment, whether you are doing it in numerical scale on a computer, you are doing an experiment, or you are doing it in the lab, whatever you are doing, there is a time of observation that is naturally associated with it. Let us make this idea a little bit more formal. So, to make it a little bit more formal, let us go back to one more very classical paper, and this paper is titled the Deborah number. Okay. And it is just a one-page paper again. So, if you are interested, you should please download this. As I said, this is just one page. It was published in 1964 in Physics Today, and I believe this is available easily on the scientific websites if you want to get it. The beginning of this paper is it's very informally written, and it sort of sets the context for the author having this discussion in the first place. So, let us leave that, and that is something I leave you for you to self study. The important thing I want to point out is this particular portion where the author is trying to set the context of the observer. And in trying to set this context, he cites a historical text, and this text is actually the Old Testament. And somewhere there it says that there is this prophetess Deborah who is there, and in her famous song after the victory over the Philistines, she sang, "The mountains flowed over the Lord." When over 300 years ago the Bible was translated into English, the translators who had never heard of the Heraclitus translated the passage as, "The mountains melted before the Lord." Okay. And so it stands in the authorized version. Anyway, the point being that the idea that is being proposed here is, the scientific idea that is being proposed here is that even mountains can flow. If you have an observer who is patient enough and who is observing things at a time scale of say millions of years, even the mountains can appear to flow. So, what is a solid? What is a fluid in that case? And to make this discussion a little bit more quantitative, Rayner goes on to introduce the idea of the Deborah number, where the Deborah number is now defined as the time of relaxation divided by the time of observation. The time of relaxation is a number that is associated with the material. The time of observation is a number that is associated with your observer. So, now the observer explicitly becomes important on trying to decide what the material response looks like. Okay. And I must clarify that this is a dynamical point of view. We are assuming that there is a force that is being applied on a material, and that under the application of this force the material is moving, and because of that there is a displacement of some sort that is happening in the body. Okay. So, that is sort of implied in our discussion. You can always also have an equivalent discussion, not necessarily fully equivalent, but related discussion happening from a thermodynamical perspective, where you do not discuss the material behavior under the action of external forces or motion, but rather you just discuss the thermodynamic state of matter. Okay. So, we are not taking that because you will see that we are going to be trying to develop the equations of motion. So, it is important to develop the dynamical sense here. Okay. So, we have gone through the pitch drop experiment. So, now we can come to the Deborah number, and in the original definition by Renner, we have Deborah number defined as the time of relaxation and the time of divided by the time of observation. Just note that we have made one important change here. The Deborah number is defined now as DE instead of just D as in the original manuscript, and the reason is we are trying to keep things also consistent, because for example Reynolds number is given the short form RE, Knudsen number is given the short form KN, right. So, this keeps things consistent for all cases. Okay. So, now the question is, what is lambda? Okay, let me, before coming to this, let me write this here. So, we define the Deborah number as lambda divided by the time of observation. Okay. So, the question is, what is this lambda? This is the response, this is a time scale associated with material response, and T observation is the time of experimental observation. Now, the question is what, so this tells you that lambda is something that is associated with the material behavior, but let us make this a little bit more explicit. So, lambda is the time scale of the viscoelastic material response or in most cases this implies most materials do not have a single time scale associated with them, but they have a whole range of time scales that is associated. So, if you have a whole range, then lambda refers to the largest time constant describing molecular relaxations. It could, so lambda could mean this, or it could also mean some averaged value of response time as determined by linear viscoelasticity. Or, so here I must say that I am jumping the gun a little bit, because I am not describing exactly what I mean by the largest time scale of molecular relaxations, etc. But please, let us just go with the flow. What I will do is in the later classes I will exactly mention what these molecular relaxations imply, or what is meant by linear viscoelasticity. Okay. So, right now I am just trying to give you an idea of that this lambda could come from multiple sources, or some time constant that appears in a constitutive relation ship. Okay, so hopefully that so we can see that lambda is in some way related. I mean, from the definitions, although we have not discussed these specific molecular relaxations or linear viscous elasticity yet, we can see that the way we are defining lambda, that it is in some way associated with material response. And the T observation here, okay, this is a time scale that is associated with the observer. So this can either be a time scale associated with experimental measurements or time scale associated with the flow now. This later definition of the time of observation as a time scale that is associated with flow is often used because sometimes there is no natural experimental measurement time scale that is associated. So, for example, if you are doing a numerical simulation or a theoretical problem solving of this viscoelastic response, then you might not have an experimental time scale associated with your investigation, but you will still have a time scale that is associated with the flow under consideration. We have already clarified that we are interested in looking at the response of the dynamical response of materials, right. So, response of a material under the action of a external force. So, this time scale is associated with flow, and in that case the Deborah number gets modified as lambda by T flow. We will see different examples of how to determine the time scale of flow in a few minutes right now, but this change is also very important. Now, what is T flow? So, this question arises. And T flow could be some time scale that you associate with the flow. It could also be it can be the reciprocal of the shear rate lambda dot can be taken as a flow time scale. Right. Usually, this is usually done for steady state flows. Now, if you do this, if you take the time of flow as the reciprocal of the shear rate, then you can define an alternative number. So, this is just the Deborah number, but in this particular case you are taking the time scale of flow as the reciprocal of the shear rate. And in this particular case, this number is often referred to as the Wiesenberg number. Okay. So, this is okay. So, this does help us in setting the stage for discussing what exactly is a solid and what exactly is a liquid. So, we are discussing simple liquids or crystalline solids. Now, in the dynamical sense, when maybe you remember from your undergraduate fluid mechanics class that in a dynamical sense, if you have a simple liquid, the idea was that if you apply a shear force on it, the fluid begins to flow immediately, and the emphasis is on immediately, which means that the time scale of response is infinite. So the material responds as soon as you apply a force, and it starts flowing. Okay. So here, if I have to go back to this, in the if lambda tends to 0, then the Deborah number, or you can also have Deborah number tending to 0 with the time scale going to 0. So if Deborah number tends to 0, then the material behaves like a fluid. Okay. If Deborah number tends to infinity, in what physical situation would you anticipate Deborah number going towards infinity? For example, if you take if you keep a solid body and then you apply a shear force on it, then the body, the way we understand a solid is a body when we apply a shear force will immediately give some strain, but then it will never flow anymore. So there is some instantaneous response, but after that there is nothing else. We will see it in a little bit more quantitative sense in the next few lectures, but that is what happens in a solid body. So if Deborah number tends to infinity, then we can say the material behaves like a solid. And of course, if it is a soft matter, generic soft matter or viscoelastic material, then you will have a finite Deborah number associated with it. Okay. So we now see that the idea of a simple fluid or a simple solid has the intuitive idea of a simple solid or a simple fluid has a more mathematically quantitative formulation that we can apply. Okay. So now let us seal the deal with a few good examples, because we have been doing a lot of discussion, but let us see some examples. So sample problem. So you have let us say there is a sphere which has a radius r, and there is fluid that is coming in at velocity u infinity. Okay. This fluid is a fluid such that it has a known relaxation time scale associated with it. So lambda is given to you, okay, and you are asked to determine the Deborah number for this particular case. So if you have to determine Deborah number, then you will say that it is lambda by T observation, just like we have done before, or T flow. Now the natural situation here is that there is not necessarily T observation associated, but there is a time scale of flow associated. And this time scale of flow is what? It can be given by u by r infinity. So my Deborah number now becomes lambda u infinity by r. So here now let me give you another example problem where I will flip things. So in this example the fluid is flowing over the sphere, but let us create a situation where there is a sphere again of radius r, and there is fluid around it which is in quiescent state. So this is our example 2, and this sphere is rotating at a given angular velocity omega. So again the question is, what is my time of flow? Lambda is obviously again given to you, so the fluid relaxation time scale is provided. So this, in this particular case, 1 by omega is a natural time scale that is associated with this situation. So we can just say it is omega into lambda. Okay. So this is how you can get the Deborah number. I will leave you with another example problem, and I'll ask you to think about it and get back. We'll get back in the next class with the actual answer. Now let's say we have two spheres, and one has a radius r1 and the smaller one has a radius r1, the larger one has radius r2, and this inside region is filled with fluid. Again, the fluid has a known relaxation time scale lambda associated with it. The internal sphere is rotating at omega. Okay. So just to recap, simple problem, you have two concentric spheres. The sphere inside has a radius r1, the sphere outside has a radius r2, and there is fluid here, there is a relaxation time scale lambda. This is rotating at omega, and you are asked to find out what is the Deborah number in this particular case. Okay. So I'll leave you with this problem to think about, and we'll come back to this problem in the next class. Okay. Okay. Thank you very much.